Hi guys, we're at the final stage now of cellular respiration, oxidative phosphorylation. Oxidative phosphorylation is where the majority of ATP is made. Through the previous stages, you might remember, and if you don't, look at the other videos, you remember that we've made a tiny bit of ATP, but lots of products like reduced NAD, and I've been saying they're going to go to this stage. And we're now at this stage, so we're going to make sense of what's been going on throughout the whole videos. It's quite a long journey, but we're nearly there now. So, all the stages we've had, we've had glycolysis, the link reaction, the Krebs cycle, and they've all made various products. Now, this table's important, and you see this quite often. So, we're just going to fill some of it in. So, in the glycolysis stage, the first stage, we produced a net profit of 2 ATP. A net profit of 2 ATP. It actually made 4 ATP, but it requires 2 ATP at the beginning. We also made two reduced NAD. In the link reaction, we didn't produce any ATP, but because it happened twice, again we produced 2 reduced NAD. And in the Krebs cycle, we produced 2 lots of ATP. Again, the Krebs cycle happens twice. 6 reduced NAD and 2 reduced FAD, something that we hadn't come across earlier. Now all these convert, apart from the ATP, these NADs and FADs convert to how much ATP they're worth. But we'll go back to that in a minute. So oxidative phosphorylation happens in, I'll draw it quickly. If you remember the mitochondria, we have the mitochondria. Made a right mess of that. Doesn't quite look like that, but it's got these folds of Christie, and what this drawing is depicting is this area here, the outer membrane, the inner membrane, and this intermembrane space. So what we've got here is the outer membrane, which means out here is all the cytoplasm of the cell. We have the intermembrane space, and then what we have in here is the matrix, where the link reaction and the Krebs cycle has taken place. These circles here, so this is the inner membrane. Okay, if that's all right. This is the inner membrane. Again, this is all in the introductory video to respiration. What we have here are electron carriers. Okay, so electron carriers. So it's number 1, number 2, number 3, and these form an electron transport chain. Okay, so an electron transport chain, which means you get electrons moving across, and as they move across, they lose energy. Here, this yellow thing is ATP synthase. And ATP synthase synthesizes ADP plus its organic phosphate back into ATP. So this is the thing that makes loads of ATP, and that's what you need to remember. It makes loads of ATP. Oops. Just move this out of the way. Okay. so what happens before we've made ATP, and these are just ATP, so that's no problem. What happens in this stage is what happens to these reduced NAD and reduced FAD. And what they do is they travel from the Krebs and the link to here. And you've got your reduced NAD comes here, and it drops off the hydrogen it's been carrying, and that hydrogen gets split, and hydrogen's only got a proton and electron. So what happens is the electron goes in here. Sometimes you see it drawn down here, but I find that confusing with photosynthesis. So the electron's gone in there, which now leaves us with just our proton. Okay, so the hydrogen gets split, the electron goes in the electron transport chain, and the proton gets left inside the matrix. What happens is this electron travels down these electron carriers, losing energy. So sometimes you'll see it drawn like this, with it going down in each one. But in this case, I'm just going to draw it as a diagonal line. Okay, so it loses its energy. Okay, do a little minus sign. As this keeps going on and on, you're going to get a little build-up of these protons, these hydrogen ions. And as this electron loses its energy, it allows these to go into the intermembrane space. So as these electrons lose their energy, the protons fill up inside the intermembrane space. And what that causes is an electrochemical gradient. And it's basically a concentration gradient of these in here, of these protons, hydrogen ions. And what happens is, because of this place gets full up, and it gets proper fill up. And they try and escape and go back to here. So there's less in here than there is out here. So the only place these hydrogen ions can go is through the ATP synthase. And as they go through it, as ADP comes in, the movement of these through ATP synthase sticks this phosphate together, and you end up with your ATP. And that is where the majority of the ATP comes from, the vast majority. But that's not the end of the story. What happens now, because these need to go away somewhere, otherwise we'll just end up with loads of these in the mitochondria, probably pop. So what happens to this proton now is half, I'll draw it over here because that's going to get confusing. Half oxygen comes in, that's what you breathe in. The oxygen's coming from the blood that you've already breathed in. And this electron that's travelled down and lost energy joins on, okay? And then this combination of that makes H2O, which is what you respire out. So that's respiration as a whole. You've got your reduced NAD coming in, reduced FAD also comes in here. It's just a bit of a lesser molecule. I'll explain what I mean by that in a minute. This does the same thing. They both drop off this, and that gets split. The electron goes into electron transport chain and loses energy. As it loses energy, these protons pass through into the intermembrane space. And as they pass through into the intermembrane space, they try and get out. They go through the ATP synthase, which synthesizes the inorganic phosphate to the ADP, which makes all your ATP. And then the electron joins to half an oxygen molecule and to the proton that's come through, and then you end up with your water, and that's that. This is this thing about electrons going down is chemoosmosis, and you see that in photosynthesis as well. So if you've seen that video, a lot of this terminology here is actually quite the same. Okay, I hope that makes sense so far. So it's quite straightforward. It's just these reduced NADs carrying this, sending it in there. They all get pumped into here. The only place they can go is back out here, and then some oxygen comes to stick it together with it to get rid of it as water. Straightforward. Now, what I was saying before, we haven't got a conversion rates of ATP worth. Well, 2 ATP is worth 2 ATP because there's 2 ATP. And there's another one there, 2 ATP. But reduced NAD and reduced FAD, you don't know the worth, so I'm going to tell you. What you've got is reduced NAD is worth, right up here, reduced NAD is what one of them equals about 2.5 ATP, and the reduced FAD is 1.5 ATP. So you can stick that in. So you can stick that into your table now and you can work out your worth. So we had 2 reduced NAD, so 2 times 2.5 equals 5 ATP. The same again, 5 ATP. We have 6 here, so 6 times, 6 times 2.5 equals 15. And then you have the FAD, which is only worth 1.5, that's why I say it's lesser. We've got 2 of them equals 3. You add up all these ATP and you end up with 32 ATP. So you get one glucose molecule that has 6 carbon will equate to 32 ATP profit. Now, the confusing bit, in some textbooks you'll see 38 ATP, you'll see 28 ATP, you'll see 30 ATP. This is where they all come from, and I can briefly explain why they get these different numbers. If you say 34 ATP, they're not counting the net profit, they count the 4 produced in glycolysis and not the 2 that's recycled. The 38 ATP is these numbers rounded up, and 28 ATP is, I can't remember, but you get them in all different places anyway. So this is the one you want to use, and in the British specs for A levels you want to use, and this ain't far wrong. Okay, so that's how we end up with 32 ATP from one glucose molecule. And the formula for respiration is, I don't think I've done it anywhere yet, your glucose molecule plus the oxygen, and the oxygen only comes into play at the end to get rid of the protons. And what you get from this is your CO2, which was waste, your water, which comes out as respiration, but also your energy, your 32 ATP. I hope all that makes sense, and there's probably over an hour's worth of videos now explaining respiration, so you might need to go over them again.